go ahead and introduce. Next up, we have Lucian Popescu from the University of Lisbon.
Test, that's good.
And as soon as this slides up, he'll tell us about exploiting undefined behavior.
So, right, just a second. Cool. Hello, everybody. Thank you for being here. Today, we are going to talk about undefined behavior, or UB for short. What it is, why it exists, how the compilers exploit it, and most importantly, what happens if we try to remove it. I'll present the first study on the performance impact of undefined behavior optimizations. So, first, let's start with a real bug. Some of you may already be familiar with this Linux kernel example. At the first glance, everything seems okay. A pointer called tune is created, and if it's null, the function returns an error. However, there is a big problem with this code. The pointer is dereferenced before it is null checked. And what does that mean from the compiler's perspective? Well, dereferencing the pointer means that it must not be null, because otherwise the operation wouldn't make sense, right? And consequently, the if check is deleted, because the compiler already proved the validity of the pointer, so it doesn't make sense to make the check one more time. The result, a security vulnerability in the Linux kernel. Fortunately, it was quickly fixed, and the fno delete null pointer checks flag was added in both GCC and Clang to fix this problem. However, the key point is that compilers, this is not an isolated case. Compilers are designed to assume that our programs do not contain undefined behavior. So you might wonder, if UB leads to security vulnerabilities, then why would the standard allow it? And the answer lies in the design philosophy of the language, which is solely based on performance. We want the language to be as fast as possible so that we can get the most of our hardware. However, there are some problems with that. First, some operations don't have the same semantics on all hardware architectures. Take shift overflow, for example, when you shift an integer by 32. x86 uses only the 5 bits of the shift amount, while ARM zeroes the result out. Imposing a single uniform semantics would either, would result in inefficient code generation and would penalize the other architectures. The other problem is that proving memory safety properties is too hard in the general case. Take, for example, array of index. The compiler needs to prove that array is allocated, that index is in bounds, and that array is not null. So by making those cases undefined behavior, the compiler can assume that they never happen, and it becomes the responsibility of the programmer to actually check that those corner cases of the language are never hit. So to sum up, performance is the sole reason for the existence of undefined behavior. And to see that in action, let us take a look at this loop. The key detail in this example is that we are running on a 64-bit machine where the size of I is 4 bytes and the size of P is 8 bytes. So at every step, we need to do a sign extension for I from 32 bits to 64. However, this, as you can imagine, is bad because it's slow and repetitive. We would like to be able to do the sign extension only once at the beginning of the loop, and that's it. Essentially turning I and N into longs instead of ints. So this simple trick, this simple optimization brings a 2x performance boost on a simple micro benchmark on my machine. But the key detail is that this optimization is only possible if signed integer overflow is undefined behavior. And to understand why, let us take a look at this sign extension table. Sign extension is only possible if for values that do not overflow. As you can see, the final example is wrong. But since signed overflow is undefined, the compiler may assume that it never happens and the optimization becomes sound, allowing us to do the sign extension correctly. So we saw that this UB optimization is great for micro benchmarks. It brings a 2x performance boost with just a simple modification. But can the same be said about real-world programs? I mean, can the same performance boost be ported to real-world applications? And more importantly, can compilers evolve in such a way that they don't need undefined behavior to prove that this optimization is correct? So those are questions that we are trying to answer in this study. Signed integer overflow is not the only UB out there. There are many, many of them, but we group them in 3 categories. First, we have UBs which compilers directly exploit. For example, dereferencing a null pointer or dividing by 0. So because those things trap on most hardware architectures, the compiler chooses to immediately exploit them aggressively as undefined behavior. Next, we have UBs for which compilers offer stronger semantics like signed integer overflow or reading an uninitialized variable. Those in general produce bogus results which then can be propagated through the program and enable other optimizations. And finally, we have UBs which compiler treat, which have more defined semantics, let's say, like strict enums and mem copying 0 bytes from null. Technically, they are undefined behavior, but compilers, if compilers optimize them too aggressively, they might break too many programs in real life, so they choose not to do that. So to sum up, we have aggressive UBs and we have more conservative UBs. But what we saw in recent years is that there is a growing trend in defining some of the UBs, like giving them stronger semantics. C++'26 will add a new type of behavior, which is called erroneous behavior, which is stronger than UB, and compilers are recommended to diagnose it. Like reading from an uninitialized variable would become erroneous behavior. C++C23 adds checked integer operations to help programmers avoid signed integer overflow UB. And the addition of the fno delete null pointer checks flag is also yet another example of how to give defined semantics to UBs. However, there is a problem. We don't know the performance impact of those changes. And I repeat, UBs are great for micro benchmarks, but do they behave the same from real-world workloads? And can the compiler evolve in such a way that they don't need UB to prove optimizations? We quantified the performance impact of undefined behavior optimizations. And we think it's also worth it to note that we only focus on performance. We don't take necessarily into consideration security implications or developer productivity implications, only performance. To do that, we developed the following experimental setups. We have 18 UB categories, which are controlled by compiler flags. We have 24 real-world benchmarks, which are security performance-sensitive applications from diverse application domains. And we run those benchmarks on 3 CPUs, AMD, Intel, and ARM. These are the 18 flags that we gathered. We divided them in 5 categories, with pointers and memory having the most flags. We started with a copy of Clang 16, which already implemented 6 flags like frapv, which gives defined semantics to signed integer overflow, and fno delete null pointer checks, which allows storing and loading from the null address. We also added 9 new flags in Clang, like fconstraint shift value, which protects us against shift overflows, and fdropAlign attribute, which protects against misaligned loads and stores. Since the intermediate representation of LLVM is not expressive enough, we also had to add 3 LLVM flags to directly control the behavior of the optimizer. 0 uninit loads does that. It replaces all loads from uninitialized variables with 0 loads. Next, I will show 2 examples of flags that we implemented. First one is from Clang, fconstraint shift value. This is the classical shift operation in C, which normally is translated to LLVM as a shift left instruction. However, the problem is that if B is greater than 32, this is UB. It will return a bogus value. So to protect against that, we add an extra instruction, an AND instruction, to make sure that B is also in the is always in the defined behavior range. So on architectures like x86, this doesn't have any binary performance impact because we are basically encoding the same assumption in the IR and in the assembly code. That is, use only the 5 bits of the shift mount. This is an NLVM flag, 0 uninit loads. This function clearly returns UB. And the interesting thing to see is that with and without the flag, the IR is the same. We have an alloca, a load, and the write instruction. The only thing that changes is the behavior of the optimizer with regards to the load. It will return 0 when the flag is enabled, so that we don't get UB. These are the benchmarks we used in our tests. As I said, we try to have a diverse set of application domains like audio-video encoders, text processing, compression algorithms, SMT solvers, and even compilers. We compiled over 7 million lines of code and used Phoronix test suite to gather this set of benchmarks. So next, let's get to the results. First, I will present the binary size impact. As I said, we used 3 architectures, and we compiled the benchmarks with link time optimizations and without link time optimizations. We used the 18 individual flags plus all flags combined to see the cumulative effect. And all the impact will be computed relatively to a baseline, where all UB exploitation is enabled. So these are the numbers. On the x-axis, we have the shortened names of the flags. And on the y-axis, we have the relative binary size impact. In this plot, lower means better, because when a flag is enabled, it drops the size of the binary. So on Intel and AMD, you can see that the binary size impact is relatively minimal. That's because those are CISC architectures where few unoptimized instructions can be combined into a single instruction, basically meaning that the binary impact remains unchanged. But the same cannot be said for ARM, which is a RISC architecture, and every new instruction in the IR means a new instruction in the assembly code. For performance, we use the exactly same setup, and these are the numbers. This time, higher means better, because the performance increases. So in Intel non-LTO and AMD non-LTO, we again see a relative minimal performance impact. Those are widely parallel architectures where few unoptimized instructions do not add too much overhead. However, on ARM, this is not the same because every new instruction adds overhead in the execution pipeline. However, the most important thing to see here is that by enabling LTO, we managed to recover the performance and even increase it in some cases. So this is a great thing because having the UB flags enabled, that is disabling UB, and having LTO enabled, we managed to get the same level of performance. So we try to use other techniques other than LTO to recover the performance. We analyzed 12 cases and categorized them in 5 categories. The interprocedural analysis used by LTO allowed us to recover important pointer metadata used in loop analysis. In the second category, we found out that the loop vectorizer in LLVM is not capable of computing the number of iterations without UB. So for that, we added some runtime checks to see, to still be able to vectorize the loops. However, newer versions of LLVM can already do that, so that's a great thing. We also found some unrecoverable cases. We found some improvements. And yeah, there was a bug in the program. John the Ripper used uninitialized data, which increased the size of the binary when we used the -0 uninitialized loads flag, giving a -1% degradation. So to conclude, we saw in the beginning that compilers assume that programs do not contain undefined behavior. And as you may already know, and that and as we've seen in the Linux kernel example, that's not true all the time. So exploiting UB for compiler optimizations introduces and creates security vulnerabilities. But fortunately, in the recent years, we saw a growing trend of defining some semantics for some UBs. So the question remains, what is the performance impact for this change? And in this study, we've shown that for the cases that we analyzed, the impact of defining UB is minimal. And what's most interesting is that we were able to recover the performance using UB-free techniques. Thank you very much.
Okay, thank you. Kangukji from the UT Dallas. I think this is really practical and an important problem. Thanks a lot for your research. I have two questions.
Yeah.
One is about about the hardware architectures that you covered. So I saw the Intel, basically x86. Mm-hmm. Did you explore the other architectures like ARM or the RISC-V or those kind of things? Second thing is that I've been aware that there was compiler passes, like for instance UBSEN, that was designed to protect the programs from the security vulnerabilities with this. Did you include those passes for your evaluations?
Yeah, when designing the flags used for optimizations and when using the already extreme flags, we wanted the performance impact to be somehow minimal. So as you saw in the -0 on init loads, we didn't set all the memory that was uninitialized from the beginning, so that we don't have an unreasonably big impact. So that's why we didn't use fsanitizer, because it would have added too much checks. So instead, we wanted to go for solutions that have reasonable performance impact. Okay, thank you.
Hi, Vadim Zaliva from Tufts. I have a. Did it happen for you after disabling some this UB checks that test will be failing, crashing? For example, an aligned memory reads on some architecture, I think on earlier ARMs, they trap. Is that happened to you, or all the tests passed with UB disabled?
No, we didn't see any crashes when disabling this kind of UB, meaning that the optimizations were not putting the code in a state that, I don't know, it would memory crash or do other kind of bad thing. So we just wanted to see how optimizations behave with regards to UB, either or not the code contains it.
Thanks.
Hi, Derek Dreyer, Max Planck Institute. Very interesting work. So did you consider multi-threaded programs or not? I wasn't completely sure.
Yeah, we consider multi-threads programs.
Okay, did you consider data race UB? Because with multi-threaded programs, right, data race UB is needed for allowing memory reorderings. So I was wondering if you tried disabling memory reorderings.
No, we actually didn't touch that part. And in the benchmark suite, we wanted mostly to focus on single-threaded benchmarks and only have a few multi-threaded, because it was easier to actually benchmark the code, because multi-threading also adds some noise, which we wanted to reduce to a minimum. So, yeah, that
okay,
was.
So I guess, can you speculate on whether on the performance impact of disabling memory reorderings based on your work here, or would you really need to test that?
Yeah, I guess kind of needs testing, because that was the motivation for doing this study, because theoretically we could assume some things about how those optimization works, but without tests on real-world software, not on micro benchmarks, we could know exactly.
Okay, thanks.
Thank you very much.
Great. Let's thank Lucian again.
Thank you.